Hi folks, my name's Tim Gross. I'm an engineer on the Nomad team. Today I'm going to talk to you about Nomad's multi-cluster deployments. It's a new feature that we shipped in Nomad Enterprise 0.112. But to set the scene, I want to talk quite a bit about the scalability and fault tolerance in Nomad, and some strategies for scaling up your Nomad deployments. So if you're not a Nomad Enterprise customer, there should be plenty here for you too. Okay, you want to deploy your app around the world. Maybe your users are geographically distributed and you want to provide an equally fast user experience for all of them. Or maybe you have EU customers who enjoy strong privacy protections and you need data sovereignty. Or maybe you're a large enterprise with both cloud and on-prem data centers. Or you've just acquired another organization and now you find yourself in a multi-cloud situation. No matter what the reason, if we're going to scale Nomad around the world, we're going to need to dive a little bit into Nomad's architecture. So every Nomad cluster is divided into servers and clients. Clients are where you run your workloads. So those might be Docker or Podman containers, JVM applications, raw exec processes, KVM virtual machines, whatever Nomad task driver you want to run. And a cluster can have many clients. There are clusters with thousands of clients. The servers are the control plane, though, the brains of the cluster. And this is where most of this talk is going to be about. A production cluster of Nomad always has 3, 5, or 7 voting servers. And servers have to agree to what jobs they're going to run on clients, and they come to an agreement on what that is with an algorithm called Raft. Now, you might have heard of Raft before. We love Raft here at HashiCorp. Raft is used in Console and Vault for consensus in their storage layer. It's also used in products like etcd, which is the data store used in Kubernetes. So why no more than 7 voting servers? Why not just scale out the servers as much as we want? Well, it's important to note that in Raft, all consensus has to be serialized through the leader. Now, Nomad does a bunch of clever optimistic concurrency tricks to make scheduling decisions really fast despite that. But at the end of the day, in order to persist a decision in the Nomad state store, the leader has to replicate the Raft log to a quorum of followers and receive their acknowledgements before it commits the entry. And so Raft has some implications for scaling out Nomad in other ways. Every follower receives every log entry. So the total storage and bandwidth requirements are going to grow linearly with the number of servers in your cluster. And when you're tuning the timeouts for Raft, the time it takes to commit to a quorum of followers, what we call the broadcast time, needs to be well under the election timeout, which in turn needs to be well under the expected mean time between failures. And those failures can be either like the failure of a server node or a network partition. Otherwise, Raft is going to lose quorum and it won't be able to make forward progress on decisions. But as you add more server nodes, the likelihood that any given write is going to experience an outlier latency and break that equation grows linearly. And so in practice, what this means is that Nomad servers in a Raft cluster need to be pretty close together, within about 10 milliseconds. To get that kind of latency, your cluster is all going to have to be in the same physical data center. Now, your larger cloud providers, AWS, Azure, have built groups of data centers close together geographically, and they've networked them together in such a way that you can treat them almost as if they're all in one big data center. The cloud providers refer to those as regions, and so Nomad cluster is referred to as a region. And you'll hear me use cluster and region interchangeably throughout the rest of the talk. So if you're going to deploy to multiple regions, there's a bunch of different strategies you can have. And each strategy has different trade-offs between scalability and overhead. If you're a small organization, you're just getting started, you're a startup, and you're planning on growing a lot in the future, start simple. Start with some of the first ones I talked about, and you can always transition to a more complex deployment later. Nomad is pretty good about not making you start over from scratch. So the first approach you can take is to centralize your servers together in one region and then geographically distribute the clients. Unlike the Nomad servers, the clients don't participate in the Raft algorithm, so they don't need to be that close to the servers. If they're a half second away, no big deal. One use case we've seen for this is in IoT applications, so distributed across farms or industrial sites. Nomad clients at each site can run applications that communicate with the sensors in their local network, but the deployment decisions about those applications are all controlled from the central set of servers, the central region of servers. A variant on that strategy is to take advantage of Nomad Enterprise's read scalability feature and to distribute non-voting servers. So long as you've got those non-voting servers so that they're not running schedulers, they can act as kind of like a local proxy to clients in their network. Clients register with the non-voting server local, and then those servers will forward their RPCs to the centralized leader. Now, the problem, of course, with a central region of servers is it becomes a single point of failure, right? If that region loses power, or if it loses connectivity, you've lost control over all the clients. So the way to avoid a single point of failure is to run isolated regions. So that's fully independent Nomad clusters with 3 to 7 voting servers in each one. The regions aren't in the same raft cluster, they're just too far apart. The speed of light is too slow to get between Bangalore and Amsterdam in less than 10 milliseconds, by quite a bit actually. But that's okay, because what it does is it provides fault isolation, right? So if something goes wrong in one region, you don't need to worry about it cascading to your other regions. Now, for isolated regions, though, you start to run into some administrative overhead. So you need to deploy a secure connection for each region, right? MTLS or a VPN. You're going to need to deploy that for your CI/CD systems as well. You're going to need to have separate access control policies and ACL tokens. And so if you're running a lot of clusters, it can start to feel like you're fumbling with a ring of keys. So we let you loosely join regions together with federation. In federation, you connect to one region, but it forwards your commands to another region, and we don't join the regions together in raft. So you say to your Amsterdam cluster, I have this job to run in Tokyo, and Amsterdam will pass that message along to Tokyo. You only need to have connectivity to one region at a time, and you configure your command line with only one set of ACL tokens. So you get the convenience of communication between regions. So if the region fails, that fault is still isolated to that region. But if your goal of federating the cluster is not just to reduce administrative overhead, but to run the same application across regions, you might start finding that it's a little hard to keep your regions in sync. So suppose you have 3 regions running version 1 of your application, and now you want to run version 2. Well, you'll have to deploy to each region individually or have your CI/CD system do it. But what if your regions aren't all the same size, right? Maybe they expect different levels of load, or one is a staging region. Now you need to deploy your job with a different count in each region. Or what if you want to deploy to one canary region first and wait for it to be healthy, and then deploy to the remaining regions? And while you're in the middle of that deployment, what happens if you're deploying to the remaining regions and one of them fails to deploy? Do you just roll back that region? You roll back all those regions? There's a lot of decisions to make here. So those are the kinds of problems that organizations with large multi-region Nomad deployments were bringing to us, and that's why we built the new MultiCluster Deployments feature for Nomad Enterprise 0.12. So with the new multi-region stanza, you run a single job and you deploy it across multiple regions. And it gives you configurable rollout and rollback strategies, and you can even kind of template the job so that each region gets a different number of instances of the job. Now, we knew that when we designed this feature that Nomad already had the right design for federation, right? We wanted to keep clusters fault isolated. We wanted to be able to have very high performing scheduling decisions. We definitely did not want to impact how Nomad worked for your single region use cases. We wanted to keep coordination low. We didn't want to make some kind of cluster of clusters that would make reasoning about correctness difficult. Raft, again, doesn't scale to this kind of thing. And we wanted to do so without introducing any new operational overhead for you as the operator. We didn't want to have an external coordinator, right? Unlike Kubernetes. So multi-region deployments leverage mostly 2 existing features of Nomad. The first is RPC forwarding. So any message sent within a Nomad cluster might be forwarded to one or more other servers. The most common case of this is what we already talked about, forwarding to the leader, right? Because that's where we originate all our Raft entries. So when you connect to one of the followers, it's always going to forward that RPC to the leader. And then there are some commands like Nomad alloc exec or Nomad alloc logs that forward from the server to a specific client agent where the workload is running. And in federated clusters, we have a region flag that tells the server to forward the request to servers of a different region. So for multi-region deployments, we just reuse the same mechanisms so that we have region-region RPC without having to create some kind of like new cross-region discovery process. And this also helps reduce the overhead of managing access control. In a federated cluster, one region acts as the authoritative region for ACLs, access control lists. So ACLs that are written to that authoritative region are replicated asynchronously to all the other regions. And so that lets you create Nomad API tokens that are scoped only to one region or scoped globally. And we'll need those global tokens for multi-region deployments. The second component we need for a multi-region deployment is the deployment watcher. This is a routine that runs on every Nomad leader that monitors deployment states. So in a single region deployment, we have this state machine. Single region deployments start in a running state and they can transition to either successful, failed, or canceled. While the deployment is running, clients will update the servers with the health of their allocations, right? This one failed, this one is complete. And that's what triggers the leader's deployment watcher to schedule additional allocations, to continue the rollout or to fail the deployment. So this is an example of a single region deployments update stanza. We have max parallel set to 1, so we're deploying one allocation at a time. We have a healthy deadline of 1 minute, and auto revert set to true. So if any allocation takes more than 1 minute to become healthy, we revert the entire deployment. So in our multi-region or multi-cluster deployments, we combine RPC forwarding and the deployment watcher to come to decisions without having a full raft consensus between regions. So here's how that works. In a multi-region deployment, we extend that state machine of the deployment watcher so that every deployment, instead of starting in a running state, starts in a pending state. And so nothing happens until it's kicked off. We're going to come back to what that means in a minute, but the important thing to note in this diagram is that at this point, no allocations have started. So you as the operator send your Nomad job run to one region, and that region is going to be responsible for registering the job with all the other regions. So it's going to do all the usual permissions checking, job spec validation locally before we kick things off, just because we don't want to send a bunch of messages around if we don't have to. Each region is going to get a slightly different version of the job. So fields like region or data centers get interpolated with the values from the multi-region stanza. That receiving region is going to query all the other regions for their existing version of the job. It's going to get the version and the current check index. We're going to use the highest version of the job that all the regions know about, and we're going to forward the interpolated copy of the job to each region using that region's check index. And what that does is it makes sure that when we make an update, there wasn't a concurrent update from, say, an autoscaler or another user in that region. So we're going to wait until we've submitted every job to that, submitted the job to every region, and then we're going to go around and check that every region has a deployment in the pending state. So it's kind of like a two-phase commit, right? We've registered and then we've checked. And that tells us that at that point, every region has validated the job, it's valid in that particular region, and it's written that job to its own raft. So what happens next depends on the multi-region configuration. So let's look at kind of a minimal configuration, and we'll look at more complex ones later. So in this one, we have max parallel 1, so one region at a time, and 4 regions in this order: Tokyo, Bangalore, Amsterdam, Sao Paulo. So our receiving region is going to kick off the deployment with a deployment run RPC to max parallel regions in the order listed. So in our case, we're going to have one RPC to Tokyo. And once all those RPCs have been sent, we're going to return the success message to you as the operator. So at this point, we've made 2 round trips to every region, but because every region is scheduling and doing the scheduling work, which is kind of the expensive computational work in parallel, you can expect that a successful multi-region submission is going to return almost as quickly as a single region job, just basically a little bit at a time for each extra region. So we've submitted our job. Great. Now what happens? At this point, the deployment watcher in each region that's been kicked off is going to be in a running state. And the deployment watcher is going to go through the exact same process it would during a single region deployment. So it's getting allocation health updates from the clients. The difference is what happens when the deployment updates its total status. So once the deployment has placed all its allocations and they're all healthy, it's going to query the status of the other regions. We want to make sure that in the meantime, while we're running that deployment, that the other regions haven't failed. So it's basically a safety check. Then the running region is going to find its place within that ordered list, and it's going to send a deployment run RPC to one or more regions that come after it, such that at most max parallel regions are now in the running state. So in this case, we're going to say the next one in the list here is Bangalore, so we're going to set Bangalore to running. And once our region has sent that RPC, it's going to change itself into the blocked state. And so that means that region has completed its version of the deployment, but it's not going to consider itself a successful deployment until it's been unblocked. And that needs to happen before the deployment progress deadline, which by default is 10 minutes. We'll come back to what that means in a second. Okay, so the next region to run is Amsterdam, and then on to the last region, Sao Paulo. Okay, so the last region in our list of regions has a special role, which is to identify that, okay, our multi-region deployment is now complete. So instead of blocking, it's going to enter the unblocking state. Again, there's no coordination that just happened for that, right? It just found its place in the list and said, oh, I'm last, so I'm the one that needs to unblock. There wasn't like a leader election between the regions that had to happen. The unblocking region will send a deployment unblock RPC to all the regions. It's going to transition them into the successful state, and then we'll transition itself into the successful state. And so that's it. At that point, our multi-region deployment is complete. So now let's look at what happens if we didn't succeed. So if at any point a region's deployment fails, if it queries the status of another region and finds out that that failed, or if it sends a deployment run or a deployment unblock RPC to a region that fails, the deployment watcher will check its on failure configuration. And that's going to tell it whether it should send deployment fail RPCs to the other regions and which ones, and whether it should roll itself back. And so in this way, the failure state can be made to cascade throughout the other regions without having to guarantee that all the regions are reachable. We're going to walk through a few more examples of failure modes in a minute. Likewise, if a deployment is ongoing and an operator submits a different version of the job, we want to cancel the current deployment, right? It's just like a single region job. So whenever one of the deployment RPCs finds that another region is on a newer version of the deployment now, meaning the deployment status we expect to see there for that deployment ID is canceled, it's going to cancel its own deployment. And just like in a failure, the region is going to send a deployment cancel RPC to all the other regions and ensure that all those regions have gotten the message. So that was a bit of a look into the distributed systems logic for multi-region deployments. But keep in mind, for you as the operator, all these internals inside, for you, the experience is still Nomad job run, right? I have a job, please run it everywhere, just as it is when you run in a single region. Right about now, you might be thinking, but how does that algorithm work if your max parallel isn't one? Okay, so now instead of kicking off one region, we're going to kick off two at a time. So we will kick off by sending the deployment run to Tokyo and Bangalore. Whichever region finishes first is going to check the status of all the other regions. And it's going to know that it can send RPCs to at most one more region. So here Bangalore finished first, it sees Tokyo is still running. That means it can hand off to Amsterdam. But if Tokyo were to finish concurrently with Bangalore, it would come to the same conclusion and try to hand off to Amsterdam too, and that would be a race condition. And so it could result as being down to only one running region when our max parallel was 2. Except Raft in the Amsterdam region will have a total order of the state changes. So whichever region loses that race is going to be told, hey, you know what, I'm already running. And so it can go and kick off the next region instead. And so that way, regardless of concurrent deployment, at any point in time, we will be very close to, at most, max parallel regions running their deployments. Okay, so we've seen the workflow. Now let's look a little bit more at a slightly more complex configuration. So in this version of the job, we have two groups. We have a web group, which has a count of 0, and a load balancer, which has a count of 1. So groups with a count of 0 are going to be interpolated with a count for each region. So in this case, Amsterdam has 5 web allocations, and Tokyo will have a count of 10. But the load balancer has a specific count of 1, so that's it. That's a signal to us that we're not going to interpolate it. So we will end up with one load balancer in each region. This is also how we prevent multi-region deployments from breaking the Nomad autoscaler. The autoscaler is setting a specific count, so updating the multi-region job won't interfere with it. We can also see that we have different data centers set for each region and a meta stanza. Job specs have a meta stanza at the task, group, and job level. This is already existing. So for multi-region, we add the regional level meta. And meta stanzas are applied in order, right? So the task meta overlays the group meta overlays the per region meta, and per region meta overlays the job level meta. Failure is always an option, so let's look in a bit more detail at rollbacks. Earlier we saw that when a region detects failure, it's going to send a deployment fail RPC to the other regions. But how does it know which ones to send it to? So the multi-region strategy block has an on failure field. The options here are fail all, which is send deployment fail RPC to all regions. That's kind of what we saw previously. Fail local, which is don't send the deployment fail RPC at all. Just fail that one region. And the default behavior is to send the deployment fail RPCs to all the remaining regions, meaning ones that fall after it in the list. This is probably the most complex behavior, but it also gives you as the operator the most flexibility. So say one region is having problems, but you want to keep the already deployed region serving traffic. Maybe the database in the region is having problems. We're out of resources in the region. We need to scale out. Or, you know what, we forgot to update the config for that new feature rolling out again. A lot of times if you have one region that's in a good state and a region fails after it, that failed state is transient, right? So we want to make sure that we're not having to roll back the entire thing automatically in the default case. So in this example, Tokyo is already run and it's in a block state. It's waiting for that deployment unblock RPC. Amsterdam and Sao Paulo are pending, and so they're waiting for the deployment run RPC, but Bangalore is unfortunately having an outage. So in the default behavior, Bangalore is going to send a deployment fail to Amsterdam and Sao Paulo, while Tokyo remains blocked. It's going to stay that way until the progress deadline expires, which is 10 minutes by default, at which point that is going to fail. Now you might be saying to yourself, what good is that? Well, a blocked region can be manually unblocked by you via the Nomad deployment unblock command. And so that marks that blocked region as successful. And so it can continue to run the workloads. And so this gives you a lever to kind of operate your application in a degraded state until you've recovered. Now, what would happen if the failed region couldn't send a deployment fail RPC? If Bangalore were to lose communication, its network was completely cut, or it lost power completely. If it loses communications or can't make RPCs to those other regions will eventually time out, right? Their deployment progress deadline, by default, 10 minutes, will expire, and then they'll mark themselves as failed. So what actually happens when a region gets marked as failed? The behavior within a region at this point is entirely controlled by the job's update stanza, just like a single region deployment. So in our previous example, we saw that each region will eventually get marked failed. So in this case, the update stanza has auto revert set to true. So when each region gets marked as failed, it's going to begin to roll back the deployment completely independently of the other regions. And so this lets us coordinate a successful rollout between regions, but we're going to fail safe and assume that we can't coordinate in the case where a single region's deployment has failed. We can use this interaction with the update stanza to build more complex failure behaviors. So the blocked region in this case is running version 2 of our job, and the pending regions are still running version 1 of our job. The failed region could be in a lot of different states. So maybe no version 2 Alex were ever replaced, and so we're all running on version 1 still. Or maybe every version 1 Alex has been replaced already, but then the database fell over, or anywhere in between. So with auto revert, the failed regions will all make sure they're on the previous version of the job. So for regions that were pending and they were marked failed, nothing's going to change. They're already running version 1. But for the region running the failed deployment, it's going to try to roll back to the previous version of the job. And notice that means that each region handles its own rollback, so there's no coordination required during the case of failure. So that was multi-cluster deployments in Nomad. A lot of what I talked about today came from internal design discussions for this feature that I have with my colleagues Mahmoud Ali and Chris Baker on the Nomad team. So thanks to them for their contributions to the design. Thank you for your time today, and enjoy the rest of the conference.